Okay, Friday morning, 10 o'clock. Any hangovers? Okay. I'm Sascha. I'm from Mister Spex, online optician located in Berlin. I'm 50 years old, software developer since around about 35 years. So starting with the C64 in mid of the 80s. And I'm today talking about how we do image optimization at Mister Spex for our product images. It begins, or it starts as a hobby project for our Slack time or Slack days with the graphics department to see how can we improve their processes, which are in most cases a little bit boring. And as a result, we have now an unsupervised process to optimize our images, product images. First of all, I talk a little bit about the what and why, then what image formats we are supporting, about quality. What is quality for us for images? It's this value when you optimize or create JPEG images, or what is it? And then finally, the squeeze out process. So how do we shrink images to the best thing? So what? Or why? In the beginning, in the early beginning, it was a manual process of our graphics department. They got a bunch of product images, whatever these product images are, we show later. And then they optimize the images, they do some color adjustments, sometimes they add paths inside these images to cut out the lenses later for different processes, for different products. And the images are exported then with a Photoshop function. Photoshop function means you can do a batch job and mark the images, and at the end, all images are falling out in an optimal way, hopefully an optimal way. Nevertheless, the fear is that the image is unsharp. And so the normal thing what the graphic department is doing, setting the quality level of Photoshop to 100%. Oof. And then we have huge images, which is not optimal for the mobile environment. So after our process, we have shrunk the image size to around about 68% for normal images, and no manual task is now there, so everything is complete automated, and which also means the person who does it before can do now complete other things in the company. So, but what about what images we are talking about? So we have product images at Mister Spex. We have so-called editorial images or mood images. This is one you say, ooh, this is a nice Ray-Ban here, please customer buy it. And then we have also info images. But we don't care about this. We have then contact lenses. With this product we are also selling. So we are selling glasses, sunglasses, and contact lenses. But contact lenses doesn't change so often. When we have a new contact lens product once in a month, it's okay. You can do this manual. But we have glasses. And we have different cuts of these glasses, or perspective, how we name it. The names are A, B, C, D, F, G. We have also G images, but this is a completely different thing. And we have try-on, where we cut out the lens, put in a new lens, and you can put it on your face to see how this frame fits. This is a dying project, because we can do it now better with 3D. And with complete films. And then we have our tinge. So when you have a prescription glass and you want to have additional colors in it, so it's a normal, maybe Ray-Ban, but you don't want to have gray glasses, but blue glasses with perception. You can see how this blue glasses normally looks on this frame. So we care only about this. And the next question we need to answer is, why do we do this? So what we see here is a Tom Ford. So it's a mid-price frame, but we have tiny lines here. So tiny, the frame is very thin. And when you resize such an image, it can happen that you see step artifacts. So when you go to normal suppliers like Akamai, they can do it, but sometimes you see these artifacts, not by Akamai, but with some others we saw it in the past. So this is a thing we must care about. The next thing is this. What is this special thing on this frame? Some ideas? Yeah, it's a gradient. Gradient is horror for lossy compression algorithms. Okay, there are modern or better algorithms now, but for JPEG, it's horrible. And this is why we, for example, can't use Goodsly. Can we see here the artifacts in the image? No. So there are huge square artifacts, so there is no gradient, but a complete artificial pattern in it, or which makes it impossible to use it. This is one of the reasons we don't use Goodsly in our process. One of the reasons is because it's horrible slow. It's not Goodsly which is slow, but Butterauchly. But these artifacts makes it impossible for us to use it in an unsupervised way. So, and then the next question we have to answer is what image formats we are supporting or we're using. Normal is JPEG. You all know JPEG. It's a lossy format. It's well supported, well understood. There are a lot of tools in background to use or to shrink JPEG images, but yeah, that's it. The second is we sometimes need to have PNGs because we need transparencies, which you see in this tinge thing. PNG is also a wide used format, well understood. We have transparency, we have indexed colors, we have true colors, we have maybe 16-bit colors, which makes sense to use it for us. And then we have WebP. WebP is a format supported by Google. Normally, all browsers are supporting it. And the question is it better than JPEG? In size, it's better. So JPEGs are normally a little bit huger, but yeah, next steps then. And when we have JPEG XR, it's a format invited by Microsoft. Okay, there's an animation problem. It's a format invited by Microsoft. It's normally the images are bigger, the quality is poorer, and the tool support is normally not existing. There was a test from Trivago. They have used JPEG XR, and they have a decrease in conversion rate, because for JPEG, for WebP, and for PNG, the GPU can do all the stuff with decoding and rendering. For JPEG XR, there's no of such support, and the processor needs it. And you know, when the processor needs it, the time or the speed of your size decrease a little bit. So these are the formats we are talking about. But can we use WebP and can we use JPEG XR. For JPEG XR, it's clear not. But can we use WebP? Because really, they're very much smaller. But then you take such an image. This is one of our bestseller images, the Ray-Ban Justin, one of the most common sunglasses out there. When you have it, it's the Volkswagen. It's a Käfer. It's a beetle under the frames. But when you resize this image, you can make the problems visible. And what you see here, this is a JPEG version. This is the output of this tool Butteraugli from Google. And this is here the WebP. And here you have all these gradient problems. And the customer sees these problems. So WebP is for us a no-go for huge images. You can use it for thumbnails, but that's it. So yes, we can use WebP. In some cases, we use it, but I will not bet that we support it in the next couple of years because new image formats are coming up. So this month, JPEG XL will be finalized. And hopefully, because Google is behind this format, it will be a complete game changer. Last time we had also here HEIF from Safari or from Apple, but no browser supports it. Now it's the third iteration of Safari, and it's still not supported, so we don't use it. Quality. What is quality for us? So first of all, you start with shooting the image. When you shoot the image, the sensor of the camera has the first loss of quality. So we are shooting with a Canon 6D, and you have there an electronic value scale from round about 12. So the human eyes can have an electronic value scale from 20 and higher. The electronic value scale is a dynamic range of the image between black and white. We can see a lot more than a camera. This has comes from the evolution because to distinguish between outlines is more important for us to survive when it's dark and we are in front of a lion, because then we must run. And this has also some effects later. But we have here first losses. Then our supplier, so we don't do it by our own. Vendor. Our vendor shrinks the images, resize the images. First, we have there, first time we have an additional loss. We have then 444 images, we come later to this, and 16-bit, so we are prepared for higher or deeper images for 10-bit screens, maybe later. So this JPEG XL, for example, will support 10 or 12-bit images and displays later. And then it comes to our process. Our process, again, it transforms the images normally into JPEG, and it will do a resize. And we are using 420 Chroma Subsampling. And we lost again because it's JPEG. JPEG only supports 6.5 electronic values, so EVS. So again, a loss in quality. Next step is we bring this image to the browser. The browser is on an external machine. He has maybe a Retina display, and you resize the images again. So in the browser, the operating system resizes the image, and the browser maybe also resizes the image. So you have again a loss in quality. And then you have the monitor, so the display itself. And it's complete out of control for us. What we can control is our combat zone here. When you're doing things with image optimization, then have always multiple monitors to test what you are doing. It should be a very good monitor, maybe such an Apple display, it's well enough. And really crappy monitors like, I have a very cheap, I think, €100 Dell monitor. It's what you see there is only mud. But it's very fine when you're fighting with image quality. So this is our conflict zone. There we play around. Ich sollte vielleicht nicht so am Bart spielen. Okay. Image quality. What is image quality? This WASP, it's a photo I took a couple of years ago, and I put it into some decoders, so encoders, JPEG encoder, WebP encoder. And you have there this quality value you can set. So I'm a command line person. I set the quality to 84%. Why? Because this is the lowest thing Goodsley supports. And you see here different images, different image size. And now I think we have a problem with the EVS of the beamer. Yes, we have. Looks all the same on the dissimilarity part. So what you do when you do lossy images, you remove parts which are not visible to the viewer, or which his mind does not recognize. But you can make these things visible. There's a tool outside called DSSIM, and with this tool you can make this visible. It brings also a value of the dissimilarity. If this is only a value, there's no scale, nothing. But it's the most important thing for this talk, next to the entropy. So every tool has its own interpretation of this similarity, because you see here, you see here different dissimilarity values, different size in the result of the image. Our value here is, or what we are doing is, we measure the dissimilarity and not the quality value of the tool, because they are always different. And for us, the quality is the value, the size to the file size to the structural dissimilarity. This is how we at Mister Spex define our product image quality. Next step, resizing. Resizing has a huge impact for the quality of your image and also for the size of your image. So when you're using a JPEG or an image magic standard resizer, it's not very sharp. So when we start with this product, we are nearly finalize it, and we try to go into production, and then the graphics department say, no, yes, the images are small, the quality is not so bad because they are not sharp. What? Not sharp. Yes, they are not sharp, because the resizer removes a lot of information. So then we took additional nearly 3 months to find the best resizing algorithm for our problem. That's always a Mister Spex problem. And we have then defined a 2-step resizing algorithm depending on the size of the final size of the image. Normally, it's always 3000 width and 2000 high. But when we have 400 pixel width images, you have a complete different resize algorithm. So resize optimization we use in 2 steps, and the operation is always implemented with ImageMagick and 16-bit PNGs, so that we don't lose so much information. Next, the image complexity. When we want to do an unsupervised image resizing or image compression algorithms, we need to understand how the image looks like. We tried a lot of different measures, but finally we use the entropy. What you see here is, this is not only a very ugly frame, but this is the a frame with the highest entropy in our product set at the time of measurement, but I checked it again before I had this talk, and it's still the most complex image from the entropy point of view. And this on the on your right-hand side is these with the lowest entropy value. I put this on my nose, and I see a little bit. No, you don't want to see it. So we have different entropy values here. You can measure the entropy with ImageMagick again. So ImageMagick is our core tool, and that's it. But now the thing is, we then start to shrink the images, or we compress the images and have a visual test where's the point where a graphics operator, where they have good eyes for this, say, okay, this is an acceptable destruction. And we come to these values. And now it's very easy in the next steps to measure the entropy and then have the rule of three to find the maximum dissimilarity which is allowed. That's everything. And then we start to check it with a few thousand of our product images, and yeah, to see, does it really work? And it looks like it works. So, and finally, we have such a table. This is everything, where we have the size, where we have the strategy to measure the destruction, because sometimes we use also Butterugly, but it's too much time consuming. And here we have the maximum and the minimum values in which range this image can be. Then, again, additional thing, Retina images. Retina is, again, a problem. Retina, you know, Macs supporting Retinas, most notebooks support Retina images, where you have the double pixel size, not points, but pixels. And in some cases, because the browser resizes it, you resize it, the operation system resize it, we have matte or blurry images on our product listing page. But currently only for Macs, so Mac desktop is not the most important thing for our customers. So currently we can live with it. Yes, we are sorry. It's based on our numbers, and when the numbers are below 5%, sorry, I don't care. For desktop, below 5%, so no, don't care about it. Nevertheless, what we find out, but not fully understood yet, so this is a complete new thing, is we reduce the Retina images 10 times more than the not Retina images. They are looking shitty when you see it in your browser or in your image program where you view your images. But the browser and the operating system, they shrink it again, and then it looks nice. And I don't exactly understand why. It works well with JPEG. It doesn't work with WebP. WebP, they are looking then also shitty. Coming out is that the Retina images are only 11 to 17% huger than the not Retina images. For desktop, it's possible to use it because we have a Wi-Fi, and normally it's fast enough. For mobile, it's a little bit more problematic, but on mobile phones or mobile systems, you don't have the problem yet. So this is our thing. It's yet not in production at Mister Spex, but we are working on it when I have time during my Slack days. So, squeezing out. Now we are coming to the process. The process is we have these images. They are coming from our suppliers and our vendors. They are controlled by our graphics department, then copy over into a shared folder, and then the system starts working. We use, as for JPEG encoder, mods JPEG and CJPEG 9C. They are doing a shootout. The smaller image will win. And so after the final images is created, it goes to the shrinking process. Then we measure the structural dissimilarity. It is above or below our threshold. We will redo it. Then when we find the optimal image, we do a JPEG rescan, the squeeze out again, depending on the tool, 3 to 70%. When you're doing it with Photoshop, you can resize it to make it up to 25% smaller. This rescan optimizes the Huffman table. So this is the encoding of the compressed data, or the dictionary of the compressed data. Yes, and then the image is normally done, and we send it to our S3 bucket, and CloudFront will later deliver it. So the algorithm behind, it's straightforward. When you're a software developer, it's an easy task. The important part here is step 4, where we start normally with 80% quality. So we are working with this quality value, but we are doing it only to compress the image. Then we took over the dissimilarity value. So we start normally with 80%, measure the dissimilarity, then we increase the value or decrease the value by 10%. After this, increase or decrease by 5%. And when you're after 5 steps and the final step, you have a range from 60 to 100% of this quality value of the compression tools, and that's normally complete enough. When you compress these images, you have the possibility in JPEG to use different types of Chroma Subsampling. So what you Chroma Subsampling is to combine colors of two square pixel thing, where you have the color value, 2 color values, and the brightness value. And when you have 444 images, you take for every pixel every value. And then you can go down and see, okay, brightness is very important for us. You know, the lion who wants to eat us. But the 422 image reduce this and takes only a part of these information. And then finally, we have the 420, which reduce this again. And you see there, this is a shrinking part. This is a shrink of the images when you only took different of these Chroma Subsampling values. The customer on his device don't see if you're using 444 or 420. Normally, yes. When it's a graphic artist, maybe he sees it, but only when he knows what the original image is. So whenever it's possible, we use 420 Chroma Subsampling to reduce the images. Next is what we are using. You know, JPEG has two modes, progressive and baseline. In baseline, it builds the images line by line. Progressive sends first a very coarse granular image, and then it optimizes the images more and more and more. This is also how JPEG XL will work later, but this is only when you're interested in. We can talk about this later. But progressive, the visual feedback for the customer is normally faster. It works very well with HTTP2, but the images are slightly huger. So our measurement is 2%. But because of the visual feedback is faster to the customer, we decide to use progressive images only. We have a little bit more time. Oh, yeah, 1 minute, 2 minutes. Then finally, we squeeze out PNGs. For PNG, we are using PNG Quant. PNG Quant is a tool from Kornelski. And with this image, with this tool, you can create from true color images indexed color images. So only 1 byte versus 3 byte per color when we are using it when we're not using 16-bit images. And so we are normally using this. We're creating these index images, and then we measure it with the dissimilarity value again. When the dissimilarity from is below a threshold, we use the normal images with a reduction of round about 70%, which is a lot when you need transparency. And they are always beating WebP. So there's no use in our use case to use WebP, which supports also transparency. And then we do again a subflee PNG behind to squeeze out the last 5%. But this is only because I can do it. There's no value. What we also don't do is when an image is below 800 byte, which we have sometimes, we don't add any more reduction, because normally an IP frame contains more data, and it doesn't make sense because and then he fills up the IP frame with 0, and it has no value to reduce it again. Finally, questions, answers. Maybe answers. Okay. Too much? Too fast? You understand everything. Fine, then thanks a lot.